Okay, we are now recording.
Okay.
Hi, this is Team 26. We will be presenting a problem. My colleagues consist of Hunter, Marcela, Kevin, and Roberto. We're asked in class to tell our patient what the chances are of them having breast cancer. The scenario goes that we come up with a positive test for this patient, with the state having a fairly low incidence of 1 case per 1,000 women annually. We have a 92% specificity and a 95% sensitivity of 92%, specificity of 95%. Sensitivity is basically the true positive rate, where what the probability is for someone that has a disease to test positive, and the opposite is true for specificity, where what the possibility of getting a negative test is for someone that actually does have the disease. Hand it over to my colleague.
Okay, so this is a contingency table. Generally, the test is going to be on the left. The test, positive or negative, is going to be in the left-hand column. And then at the top is going to be disease or no disease, where we have labeled cancer and no cancer. It's important to know as well that the marginal probabilities are the sum of the rows and columns, which is what we're representing in the sides, on the margins of probability of having disease, no disease, and having a probability of the probability of having a test positive and test negative. So as we can see, this is how you would label it. We can go on to the next slide. So in here, with the sensitivity and the of 92% and specificity of 95%, we can see how we were able to come up with having a 0.0092 of having positive mammogram that results in a positive cancer result, or having patients that actually had cancer. And in the margins at the bottom, we can see that you have a 0.001 probability, and then the 0.999 probability, whether having cancer or no cancer, and the probability adds up to 1. Go ahead.
So using the conditional probability formula, we have the probability of having the disease with a positive test, and we take that and we divide it with the probability of a disease with positive test over the probability of a positive test. So from using the numbers from before, we have a sensitivity of 0.0092, and we divide it by the 0.05087, and that gives us a value of less than 2%, meaning that we can tell our patient that she has a less than 2% chance of having breast cancer.
Now to do it quickly, they have what we call Bayes' theorem shortcut. This will be basically you take the rate of disease times the sensitivity of 0.92 and divide it by the rate of disease times sensitivity plus the rate of no disease times a false positive, which is 1 minus specificity. So here you can see how we found the rest of the equation. So 0.001, that would be the rate of the disease. Our sensitivity is 0.92. You multiply that together, you get 0.00092. For the denominator of the equation, again, we have the rate of disease times sensitivity for the first portion of it. And then you're going to add in the rate of no disease. To find the rate of no disease, again, we took 1 minus 0.001, which was the rate of the disease, and it gave us the rate of no disease. And then for the false positive that we multiply the rate of no disease by, we take 1 minus specificity of 0.95 and get 0.05. That all comes down and it becomes 0.00092 over 0.05087, which then gives you a 0.018 or less than 1.8% chance of breast cancer.
Okay, so in conclusion, we can answer our patient's question of what's her chance of having breast cancer based off of this test with a sensitivity of 92% and a specificity of 98%, by computing the conditional probabilities utilizing contingency tables as well as applying the shortcut of Bayes' theorem. And we can answer her question saying that she has a less than 2% chance.